In this lecture, we'll talk about mathematical description of a wave. So let's look at a stretch string. So when the string is at equilibrium, this can be shown by, let's say, on x-axis. So this is my stretch string. We are considering here transverse wave. Transverse wave. During wave motion, a particle with equilibrium position x, it displays some distance y perpendicular to the x-axis. So the value of y depends on which particle we are talking about, and also on the time t. So for example, this particle point at the point A has some y, particle at point B has some y. So the value of y depends on what position of x we are talking about, because different values of x, or even time. The point A at time t is equal to 0 is, let's say, here. Time 1/8 of the period is here. So we can write it that the value of y depends on, is a function of depends on x and t, time. So you can write it as a wave function. Y is equal to y is a function of x and t. And here we can see that that particle at point B is at maximum. Point B is maximum positive value at t is equal to 0, and returns to y is equal to 0 at t is equal to 2/8 of the period t. Okay, same events occur for particles at point A and point C. Point A and point C at, so point A is here, point C is here. So same events occur at particles at point A and point C at time 4/8 of t and 6/8 of t, exactly half period after. So here is maximum, here is maximum, point A is maximum, and then it becomes at the equilibrium position. Same to point B was maximum here, and 1/4 of period it comes to equilibrium position. So cyclic motion of various points on this string are out of step. So different points on this string are out of step with each other by fraction of a cycle, right? And these differences are called phase difference. So phase difference, you can say phase difference is the fraction of the cycle, right? Fraction of this cycle. Different particles different particles are out of steps, right? Are out of step. Okay. So phase of the motion is different for different points. So each point will have its own phase. So talking of that, we can say point A and point B, or point B and point C are half cycle out of phase. So point A and point B, or point B and C are half cycle out of phase, right? Okay, so let's okay, so let's say, let me write it down. So let's say the displacement of a particle at the left end this left end of the string at x equal to 0 is equal to, let's say we write it y, and x is equal to 0 or some value, and time t is given by ym sine omega t, and that the particle is oscillating in simple Harry motion with amplitude m, with amplitude, this is the amplitude, and omega is equal to angular frequency, and f is the frequency, right? Okay, and yx is equal to 0 t is a particular case when x is equal to 0. So this is my general wave function. Okay, and y 0t is a particular case of this general function. So the wave disturbance travels from x equal to 0 to some point x to the right of the origin in an amount of time x over v, and here v is the speed of the wave, Okay, so here the wave, this wave, as this is oscillates wave, is moving in this direction at a speed of v. So continue from the previous one. So the motion of point x at time t is the same as the motion of point x is equal to 0 at x equal to 0 at the earlier time of t minus x over v, right? So we can write, so y xt can be written as ym sine of omega t will become t minus x over v. Okay, or we can write negative ym sine of omega x over v minus t, right? Because sine theta is equal sine negative theta is equal to negative sine theta. Okay, and then we can write is equal to negative ym sine of 2 pi over lambda x minus omega t, right? And we know omega over v, and we know omega is 2 pi f, and v we know is lambda f is equal to 2 pi over lambda. So that's what we substitute there. Or we can write ym is equal to sine of k x minus omega t. So this is one general mathematical wave function. We found it here. Here k is 2 pi over lambda and is called wave number. Okay, so this equation says is the equation for sinusoidal wave moving in positive x direction. Okay, so if I have a wave here, let's say a couple of things here, so this wave is looking like this. Okay, the velocity v is the velocity the wave is moving. The amplitude of this is the amplitude, this is ym. Period is from here to here, that wave takes. This is one wavelength, so we call it lambda. The time t is the period, is the time to travel a distance of